31,600 kilometres. That is how close an asteroid the size of a small mountain will come to your head. On Friday the 13th of April, 2029, beneath our satellites, bright enough to see without a telescope, closer than any object of its size has come in recorded history, and the thing that has scientists paying very close attention is not the impact risk, because there isn't one. NASA and the European Space Agency have both confirmed that. What has them nervous is stranger than that. The single measurement that determines what this rock does for the next 100 years currently has 8 different answers, 3 of which nobody can tell apart, and the window to work out which one is correct closes before the asteroid ever gets here. If that has you hooked, hit the like button and subscribe to the Skylab, because we are following this one all the way to 2029. Drop a comment and tell me where you're watching from, and whether you will be under the track when this thing crosses your sky. Now, let's get into it. Part 1. The date that is already fixed. There is an appointment on the calendar and nobody on Earth can move it. On Friday, the 13th of April, 2029, at approximately 21:46 Universal Time, an asteroid named Apophis will pass closer to this planet than any object of its size has passed in recorded history. That is not a forecast. That is not a probability with error bars stapled to the side of it. It is a scheduled event, calculated to the second, and the calculation has been checked by every major space agency on the planet. The distance is where most coverage starts to get confusing, so let me clear that up immediately, because you will see 2 different numbers, and both of them are correct. Measured from the centre of the Earth, Apophis will pass at about 38,012 kilometres. That is the figure used in the dynamical models, and it is the one you will find in the technical literature. But nobody experiences distance from the centre of the Earth. We experience it from the surface, so you subtract the radius of the planet, roughly 6,371 kilometres, and you get the number that actually means something to a person standing outside looking up. About 31,600 kilometres above the ground, 6 Earth radii. That is the whole gap. Here is the comparison that makes it land. The geostationary satellite belt, the ring of communications hardware that carries a significant fraction of the world's television and weather data, sits at an altitude of about 35,786 kilometres. Apophis is going to pass underneath it. A rock the size of a small mountain is going to thread between our satellites and our atmosphere, and it is going to do it in broad view of about 2 billion people. The rock itself is not enormous by asteroid standards. NASA's published figure is around 340 metres across. The wider literature puts the mean diameter somewhere between 340 and 420 metres, and the most recent shapework, scaled against timings taken when Apophis passed in front of a background star, gives a volume equivalent diameter of 417 metres. It is a stony body, spectrally consistent with a class of ordinary chondrite meteorite, reflecting about a quarter of the light that falls on it. Its geometric albedo comes out at about 0.24, with an acceptable range running from 0.16 to 0.28. In practical terms, that means it is roughly as reflective as weathered concrete. Not black, not bright. Ordinary rock, doing what ordinary rock does. Mass is where the numbers stop feeling ordinary. Characterization work puts the bulk density well under 2 grams per cubic centimetre, with something like 40% of the interior being empty space. That is the signature of a rubble pile, a body held together by its own weak gravity and whatever friction exists between the pieces, rather than by the strength of solid stone. Even at that low density, a 400-metre sphere works out to tens of billions of kilograms. It will be moving at 7.42 kilometres per second relative to the Earth at closest approach. That is fast enough that you will see it move. This is not a dot that hangs in the sky. This is a point of light that visibly crawls against the background stars over the course of an evening and then leaves. Now, here is the part that I need you to sit with, because almost every version of this story you have encountered gets the emphasis wrong. The thing that has scientists paying very close attention is not an impact. NASA has stated it. The European Space Agency has stated it. There is no risk of Apophis striking this planet for at least the next 100 years. That conclusion is not a reassurance issued to keep people calm. It is the output of radar observations taken in March of 2021, when the asteroid was still about 17 million kilometres away, using the Goldstone Antenna Complex in California and the Greenbank Telescope in West Virginia. Radar measures distance directly. It is one of the hardest measurements in astronomy to argue with. Those observations closed the last remaining case on the books, so the impact question is answered, genuinely, properly answered. And that is exactly why the people who study this object are now watching it so intently. Because the 2029 encounter does not simply let Apophis go past. Earth is going to do something to it. When a small body passes this close to a planet, the planet's gravity rebuilds its orbit. Apophis is going to change dynamical class. Right now, it belongs to a group of asteroids that spend most of their time inside Earth's orbit, closer to the Sun than we are. After April of 2029, it will belong to a group that spends most of its time outside Earth's orbit. One afternoon, and the fundamental character of its path around the Sun is different. But the orbital change is the part we can calculate. Here is the part we cannot. Following that close approach, the uncertainty in Apophis's future trajectory increases by a factor greater than 40,000. Let me say that in plain language, because a factor of 40,000 is the kind of number that slides straight past you. Right now, Apophis has one of the best determined orbits of any object in the entire near-Earth catalogue. We know where it is going with a precision that is genuinely remarkable for a rock we only discovered in 2004. After the encounter, that precision is largely gone. A very well-determined orbit becomes a poorly known one, in which chaotic effects start to dominate. The mechanism behind that amplification is worth understanding, because it is not mysterious. It is geometry. Picture two versions of Apophis approaching Earth on paths separated by a single kilometre. Far out, that separation stays a kilometre, but as they sweep past the planet, each one is bent by a slightly different amount, because each one passes through a slightly different strength of gravitational field. The one that passes marginally closer gets bent marginally harder. They leave on paths that are no longer parallel, and every year afterwards that divergence grows. A kilometre becomes 1,000 kilometres. 1,000 becomes 1,000,000. Nothing exotic is happening. A close approach is a magnifying glass held up to whatever uncertainty you brought with you. The encounter is a lever. A small difference in what goes in becomes a large difference in what comes out, and the closer the pass, the longer the lever arm. Which raises the obvious question: if we know where Apophis will be on the 13th of April to within a fraction of a second, what is the small difference that gets amplified? The answer is not its position. Its position is nailed down. The answer is the way it is turning. Apophis is tumbling. Not spinning cleanly about a single axis the way a planet does, but tumbling in a complicated two-period motion that requires more than one number to describe. And the effect that Earth's gravity has on that tumble during those few hours around closest approach depends very sensitively on exactly which way the asteroid is facing when it arrives. That matters for one specific reason that we will build out carefully later, so I will only plant it here. There is a force acting on Apophis right now that is far too weak for you to imagine mattering. It is sunlight. Not the pressure of the light itself, but the heat the asteroid absorbs and then radiates back out a little later, after it has turned, so that the warm afternoon side pushes slightly harder than the cool morning side. That imbalance is the difference between where this asteroid will be in 100 years and where it will not be. And the size of that imbalance depends on how the object is spinning. So the tumble is not a curiosity. The tumble is the steering. That orientation is the initial condition of the entire experiment. It sets where the lever is placed. And everything downstream of the encounter runs through it. You would expect that to be the best measured quantity in the whole file. 22 years of observation, thousands of data points, some of the finest telescopes on Earth pointed at this one rock. It is not. In work published this year by a team led out of Prague, using the most extensive photometric dataset ever assembled for this object, the spin state of Apophis was found to have not one solution but eight separate best-fit models, which collapse into three families that the data cannot tell apart. Three statistically equivalent answers to the single question that determines what comes out the other side of 2029, and the window to work out which one is correct does not stay open. It closes in the middle of 2028. The 2029 apparition itself, the one where the asteroid is right on top of us and brighter than it has ever been, cannot resolve the ambiguity. And the encounter, when it comes, overwrites the very state we would have wanted to measure. That is the story, not a threat, a deadline. Part 2. What 2 billion people will see. For most of the human population, the 13th of April 2029 will be a night to go outside and look up. Apophis will be visible to the unaided eye across the Eastern Hemisphere. Europe, Africa and Western Asia sit under the track. Peak brightness is expected to reach about magnitude 3.1, in a window running roughly from 2000 to 2100 Universal Time. Estimates of the population inside the viewing footprint run to about 2 billion people. Magnitude 3.1 deserves a moment of explanation, because the scale is counterintuitive. It runs backwards. Lower numbers mean brighter objects. The brightest star in the night sky sits at about -1.5. The stars that make up the handle of the Big Dipper run between magnitude 2 and 3. So Apophis at 3.1 will be roughly as bright as a middling star in a familiar constellation. From a dark rural site it will be easy. From a suburb it will be visible if you know where to point your eyes. From the middle of a large city, under heavy light pollution, it will be marginal. It will be the first time in the modern observational era that a body of this size crosses the sky and can be watched without a telescope. I want to manage the expectation, though, because the imagery attached to this story is usually wrong. Apophis will not streak. It will not glow. It will not leave a trail. It is not entering the atmosphere, so there is no fireball, no sonic boom, no burning. What you will see is a moving star, a single point of light, unremarkable in colour, that is noticeably in a different place at the end of an hour than it was at the beginning. Quiet. Almost anticlimactic. The motion is the giveaway. At its closest and fastest, an object crossing the sky at 7.42 kilometres per second from 31,000 kilometres out will traverse a noticeable fraction of a degree every minute. For scale, the full moon is about half a degree across. So over the space of a few minutes you will watch it cover a moon width of sky, and over an hour it will have travelled far enough that anyone who noticed where it started will be certain it has moved. It is the only way you will know you are looking at the right point of light, and that quietness is the honest character of the event. The drama is not in the sky. The drama is in what the pass is doing to the asteroid while you watch it. The satellite question comes up constantly, so let me deal with it. Apophis passing beneath the geostationary belt does not mean it is threading through a minefield of hardware. The belt is a ring roughly 265,000 kilometres in circumference, occupied by a few hundred active satellites, each one a handful of metres across. The emptiness is almost total. The probability of a collision is negligible, and it has been assessed as such repeatedly. The reason the geostationary comparison gets used at all is not because of risk. It is because it is the only altitude most people have an intuitive feel for. About 16 hours after closest approach to Earth, Apophis passes the Moon, at a distance of about 95,959 kilometres. In the modelling, the Moon's gravitational influence on the asteroid's rotation is set aside entirely, because the torque it applies is roughly 1,300 times weaker than Earth's. That is a useful sense of scale. The Moon is close enough that it feels like it should matter, and it does not. A factor of 1,300 is the difference between a term you must model with care and a term you can strike from the equation without consequence. The orbital change is worth sitting with for a moment, because it is the one large consequence of this encounter that we can predict cleanly. Asteroids are sorted into families by the size of their orbits. The dividing line is the astronomical unit, the average distance from the Earth to the Sun. Asteroids that orbit with an average distance smaller than 1 astronomical unit, but that still cross our path, are called ATENs. They live mostly on the inside of our orbit, closer to the Sun, and they come out to meet us. Asteroids with an average distance larger than 1 astronomical unit, which also cross our path, are called Apollos. They live mostly on the outside, and they come down to us. Apophis is an Aten. On the 13th of April 2029 it becomes an Apollo. Earth's gravity will lift its orbit, push its average distance from the Sun past that dividing line, and change the category it has occupied since long before anybody discovered it. This is not a bookkeeping change. It means a longer year, a different set of resonances with the other planets, a different pattern of future close approaches, and a different thermal environment as the asteroid spends more of its time further from the Sun. One pass, one afternoon, a different life for the rest of its existence. Now hold that against the precision on the other side of the ledger. The nominal epoch of closest approach is specified in the technical work as a modified Julian date of 62,239.90709. That is a timestamp accurate to a fraction of a minute for an event more than 2 years away involving a rock we have never touched. The approach velocity far from Earth is 5.84 kilometres per second. At closest approach, it is 7.42. Every one of those numbers is solid, and every one of them was derived from optical astrometry and radar ranging on an object that is, at this moment, an unresolvable dot. There is a geographic unfairness built into all of this that is worth naming, because it will shape how the event is remembered. The Eastern Hemisphere gets the show. Europe watches it in the evening. Africa watches it high overhead. Western Asia catches it as the sky darkens. The Americas, where a very large share of the world's amateur astronomy equipment happens to live, are on the wrong side of the planet during the closest hours. By the time the skies dark over North America, the asteroid has already made its pass and is receding. That is not a small detail for the observing community. It means the best data on the closest approach of an asteroid in recorded history will come from telescopes in Europe, Africa and Asia, and it means a lot of very capable observers are going to spend that evening watching a live feed rather than a sky. And yes, it falls on a Friday the 13th. That is a genuine coincidence and nothing more. The orbital mechanics put the date where it falls, and the calendar happened to be underneath. It is a good line for a headline and it means nothing at all. Here is the contrast that the whole story turns on, and I want to state it as cleanly as I can. Every number describing where Apophis will be is pinned down to an accuracy most people would find hard to believe. Every number describing how Apophis will be oriented when it gets there is not. We know the position of a 400-metre rock 2.5 years out to within a few kilometres. We do not know which way it will be facing to within 20 degrees. That asymmetry is not an accident of how much attention each question has received. Both have been studied hard, by good people, with excellent instruments. It is a consequence of what the two measurements are. Position comes from radar and astrometry, which measure the thing you want directly. Orientation comes from watching a dot get brighter and dimmer and inferring a three-dimensional motion from a one-dimensional signal. One of those is a measurement, the other is a reconstruction. And if that sounds like a strange thing to care about, if position is the hard part and orientation is a detail, then what follows is going to change your mind. Because the orientation is the part that determines what the encounter does. It is the part that determines how the asteroid moves for the next century. And it is the part that has 3 different answers. So if we know exactly where it will be, what is actually left to get wrong? Part 3. Earth will not tear it apart. Let me clear away the largest misconception before we go any further, because it stands directly in the way of the real story. Earth is not going to break Apophis apart. Not partially, not at the neck, not at all. The instinct that says otherwise is a reasonable one, and it has a specific origin. In March of 1993, 3 astronomers found a comet that looked wrong. Instead of a single object, it was a string of fragments, more than 20 of them, strung out in a line that observers started calling a string of pearls. Working backwards, it turned out the comet had passed within about 40,000 kilometres of Jupiter the previous July, and had been pulled apart by tidal forces. In July of 1994, over the course of 6 days, those fragments slammed into Jupiter one after another, leaving dark bruises in the cloud tops larger than the Earth. It was the first time humanity ever watched 2 solar system bodies collide. That event is why the phrase tidal disruption carries weight, and it is why, when people hear that an asteroid is passing beneath our satellites, the mind reaches straight for that image. The comparison does not survive contact with the numbers. Jupiter has more than 300 times the mass of the Earth, and tidal force falls off with a cube of distance. A comet nucleus made largely of ice and dust, already weakened by repeated passes near the Sun, is a far more fragile thing than a stony rubble pile. Run the calculation for Apophis at 6 Earth radii, and it is not marginal. It is not close. The current technical assessment is unambiguous. At that separation, the global shape of Apophis will not significantly change, and the asteroid can be treated as a rigid body straight through the encounter. That rigid body assumption is doing something specific, and it is worth being precise about it, because rigid is a strange word to apply to a pile of gravel. It does not mean the asteroid is solid. It means that for the purposes of calculating how it turns, the pieces stay in the same arrangement relative to one another. The pile does not slump. The mass distribution you start with is the mass distribution you end with, and the modelling holds that assumption valid all the way past closest approach. Our video from the 19th of June went a long way into the interior question, into the two-lobed shape, the neck between the lobes, and the rubble pile evidence that says this object is a loosely bound collection of debris rather than a single stone. That was a story about what the encounter might do to the body. This one is a different story. This one is about what the encounter does to our ability to predict anything at all. But something does happen to the surface, and it is more interesting than a breakup would be. The tidal stresses during the pass will drive discrete seismic events, not a continuous shaking, but individual releases, producing high-frequency surface accelerations above about 1/10 of a hertz. The frequency matters. 1/10 of a hertz means an oscillation every 10 seconds or faster, which is fast enough to break the static friction holding loose grains in place. Slow, gentle flexing would not do it. Sharp, repeated jolts do. The published modelling finds that those accelerations reach magnitudes comparable to Apophis's own surface gravity. Now, that phrase sounds enormous until you put a number on the gravity. On a 400-metre rubble pile with a bulk density well under 2 grams per cubic centimetre, the pull at the surface is measured in fractions of a millimetre per second squared. A person standing on Apophis could jump and not come back. A pebble dropped from waist height would take several minutes to reach the ground. So a shaking that matches that gravity is not an earthquake in any sense you would recognise. It is enough to unstick dust. It is enough to nudge gravel. What it produces, according to the modelling, is destabilisation of centimetre-scale patches of regolith. Small downslope movements, material sliding a short distance and stopping, and underneath the material that moves, unweathered subsurface exposed to direct sunlight for what may be the first time in millions of years. That last detail matters more than it sounds. The surface of an old asteroid is chemically altered by constant bombardment from the solar wind and from micrometeorite impacts, a process called space weathering. Over long timescales it darkens the surface and shifts its colour towards the red. Fresh material from underneath has not been through any of that, and it looks measurably different when you put a spectrometer on it. So a body that has been uniformly weathered for a very long time could come out of this encounter wearing bright, unreddened patches. Those patches would be detectable from a spacecraft. And there are going to be spacecraft on both sides of the date. We have a reasonable idea of what that surface looks like, because we have visited its relatives. When the Japanese Hayabusa spacecraft reached the asteroid Itokawa, a body of very similar size and composition, it found something nobody had expected. There were almost no craters. Instead, there were boulders, thousands of them, piled together with smooth ponds of fine gravel collected in the low spots between them. Bennu, visited by NASA more than a decade later, turned out to be rougher still, so covered in boulders that the mission had to spend months hunting for a patch of ground clear enough to touch. These are not solid worlds with dusty coatings. They are heaps. Everything on the outside is sitting on everything else, held by almost nothing. That is the surface the tidal shaking is going to act on, and it explains why the predicted effect is so specific. On a solid body, a jolt does nothing. On a heap, a jolt is exactly the thing that matters, because a heap is always sitting one small disturbance away from settling. There will be no catastrophic avalanches. The tidal perturbation is too small to trigger large-scale collapse. Slight, localized slides remain possible in places where the granular structure is already marginal, sitting near its angle of repose, waiting for any excuse at all, but nothing dramatic, nothing you could see from Earth. The longer-term consequence is the bigger one, and it comes back to the tumble. Because the encounter changes how Apophis rotates, it changes the effective slope of every surface on the body. This is a genuinely strange idea, and it takes a second to absorb. On a small, fast-turning asteroid, what counts as downhill is not set by gravity alone. It is set by gravity combined with the outward centrifugal effect of the rotation, and that combination varies across the body, depending on where you're relative to the spin axis. Scientists call the result an effective potential. A slope that is stable at one rotation rate can become unstable at another without a single grain being touched. So change the tumble, and you have redrawn the entire slope map of the asteroid everywhere at once. Modelling of that downstream effect suggests roughly half of Apophis's surface could be excavated to a depth of around 10 centimetres, on timescales shorter than 1 million years, as a delayed consequence of what happens on one afternoon in 2029. The past does not smash Apophis, it reshuffles it, slowly and mostly after the fact, and here is the connection back to the thread. Every single one of those outcomes, the seismic events, the patch destabilization, the slope changes, the resurfacing, depends on how the body is oriented and how fast it is tumbling when it arrives. The same unmeasured quantity, the same 3 competing answers, which brings us to the question this entire story rests on. What is that quantity exactly, and why can nobody pin it down? Part 4. It does not spin, it tumbles. Everything you are picturing right now about how an asteroid moves is wrong, and the correction is the reason this story exists. When most of us imagine a rotating object in space, we imagine a planet. A ball turning steadily about a fixed axis. One rotation, one period, one number. Day and night. Over and over, reliable enough to build a calendar on. That is the picture, and for the large bodies in the solar system it is close enough to true. Apophis does not do that. Apophis tumbles. The technical term is non-principal axis rotation, and it means the asteroid is not turning about any one of its natural axes. Its rotation axis is itself moving. If you filmed it for a month, you would never see the same face presented the same way twice, in exactly the same orientation. The motion is closer to a badly thrown American football that wobbles end over end while also rolling, or a mobile phone tossed spinning across a room, which almost never lands the way you expected because it is turning about 2 things at once. More specifically, Apophis is in what is called short-axis mode. That describes which way the angular momentum is pointing relative to the body. In short-axis mode, the angular momentum vector circulates around the asteroid's shortest dimension. There is a second family of tumbling, called long-axis mode, where it circulates around the longest dimension instead, and the boundary between the two turns out to matter a great deal later in this story. For now, hold on to the fact that Apophis is in one of them and not the other, and that this is a genuine physical distinction rather than a piece of bookkeeping. Because it tumbles, one number cannot describe it. You need 2. The first is the precession period. That is how long it takes the asteroid's rotation axis to complete one circuit of its wobble. For Apophis, the best fit value is 27.374 hours, plus or minus 1/1000th of an hour. The second is the rotation period. That is how long the body takes to turn about the axis itself. For Apophis, that is 262.2 hours plus or minus 1/10th. Roughly 11 days. So the asteroid completes a slow 11-day turn, while its axis wobbles through a full circuit every 27 hours or so. Those 2 motions run at the same time, independently, and they never quite line up. Here is where it gets difficult for anyone trying to measure it. What an observer on Earth actually records is not the rotation, and not the precession. It is brightness. A dot in a telescope that gets slightly brighter and slightly dimmer as different amounts of illuminated surface swing into view. And those 2 underlying periods combine into a single beat pattern. The way 2 musical notes close in pitch produce a slow throb that is neither of the original notes. For Apophis, every acceptable pair of periods produces the same beat, 30.5658 hours. That 30.5-hour signal is the thing you see in the raw data. It is clean, it is repeatable, and it is not either of the 2 numbers you actually want. So the task is to work backwards. You have a one-dimensional signal, brightness against time, and you're trying to reconstruct a 3-dimensional tumbling motion of an irregular body you have never seen up close, illuminated from an angle that changes over the months of an observing season. It is genuinely one of the harder inverse problems in observational astronomy, and it is why the answer took 22 years and is still not finished. The direction the angular momentum points is the one part of this that is nailed down well. In the coordinate system astronomers use for the plane of the solar system, it sits at an ecliptic longitude of 246.8 degrees and an ecliptic latitude of minus 87.2 degrees. That second number is the important one. Minus 90 would be pointing exactly at the south pole of the solar system's plane. Apophis is within 3 degrees of it. Whatever else this asteroid is doing, It is tumbling about an axis that points almost straight down out of the plane of the planets. The formal precision on that direction is about 1 degree, but the team that produced the number added a caution to it themselves, which I find worth admiring because nothing forced them to. The real uncertainty, they wrote, is at least a few degrees. The reason is that the sun's gravity applies its own slow torque to a tumbling body, and that torque alone drags the axis around by roughly 3 degrees every 8 years. A formal error bar that ignores a real physical effect is a number that looks better than it is. That near polar orientation has a consequence we will come back to later, and it is one of the more elegant traps in this whole subject. When something points almost exactly at a pole, its longitude becomes an unstable quantity. Take 3 steps sideways next to the geographic North Pole, and your longitude can swing through 90 degrees while you have barely moved at all. Apophis's angular momentum vector sits in exactly that situation, 3 degrees from the pole of the solar system's plane, and it means certain numbers describing its motion are going to look far more dramatic than the physical reality behind them. Hold that thought. 2 more values complete the picture. The initial nutation angle, which describes how far the axis is tipped away from the angular momentum direction at the reference moment, is 19.9 degrees, and the moments of inertia, which encode how the asteroid's mass is spread out, come in at 0.607 and 0.9724 in normalized units, with realistic ranges around them and a negative correlation between the two, meaning that if one is higher, the other tends to be lower. Now, where did all of that come from? Not from a spacecraft. Nobody has been to Apophis. Every one of those numbers came from watching a dot change brightness, from the ground and from orbit, over 2 separate observing seasons more than 7 years apart. The single most valuable dataset came from the Danish 1.54-meter telescope at La Silla in Chile. Between the 16th of November 2020 and the 6th of May 2021, that instrument observed Apophis on 67 separate nights and collected 1,280 individual measurements at an absolute accuracy of 1/100th of a magnitude. That is a level of photometric precision that most people outside the field do not realize is achievable on a moving target this faint. Across those months, the viewing angle swung through a huge range, from 24 degrees to 100 degrees of phase, which means the team watched the asteroid under wildly different lighting conditions and could use the differences to constrain the shape. TESS contributed as well. The space telescope built to hunt for exoplanets by staring at stars for weeks at a time turns out to be excellent at watching asteroids for exactly the same reason. During Sector 35, spanning the 19th of February to the 7th of March 2021, it added 1,149 data points from orbit, with none of the interruptions that weather and daylight impose on a ground telescope. Then the smaller contributors. The TRAPPIST telescopes north and south observed between the 15th of January and the 13th of April 2021. The WISE Observatory's 0.7-meter instrument covered 15 nights between the 24th of December 2020 and the 7th of April 2021. The Mont Mégantic 1.6-meter added 5 more nights. A separate published dataset assembled more than 200 light curves from 36 different telescopes. I'm listing all of this for one reason. When you learn that the answer came out ambiguous, the natural assumption is that the data must have been thin. It was not thin. Apophis is one of the best observed small bodies in the sky, watched by professionals and by a distributed network of very serious amateurs, at accuracies that would have been impossible a generation ago, and with all of that the analysis produced 8 answers. Part 5. 8 models, 3 families. In an institute on the edge of Prague, a group of people spent a long time counting something that cannot be counted. The work is led by a researcher named Jurek at the Institute of Astronomy at Charles University, alongside a colleague named Vokruliski at the same institution, and a researcher named Prague at the Astronomical Institute of the Czech Academy of Sciences at Ondřejov, out in the countryside southeast of the city. The full author list runs past 20 names, spread across 11 countries, from Chile to Morocco to Massachusetts. It is the kind of paper that only gets written when a large number of people have been pointing telescopes at the same rock for 2 decades and are finally ready to put everything in one place. Their method was straightforward in description and brutal in execution. Take the full photometric dataset, Search the space of possible spin states for combinations that reproduce the observed brightness variations. Find the local minima, the parameter combinations where the fit is better than anything immediately around it. Take the 20 best of those. Then run each one through a higher resolution inversion, with more iterations to see which ones survive. That word, minimum, deserves a moment, because it is the geography of the whole problem. Picture the space of every possible spin state as a landscape of hills and valleys, where altitude is how badly a given combination of numbers fails to match the observations. A perfect match sits at the bottom of a valley. The job of the search is to find the lowest point, and the difficulty with a landscape like this is that it is not one smooth bowl with one bottom. It is pitted with hundreds of small depressions, each one a place where every direction you step makes the fit worse, even though a valley somewhere else is deeper still. Those are the local minima. Finding one tells you that you have found something. It does not tell you that you have found the answer. Alongside the spin solution, the same process reconstructs the asteroid's shape, expressed as a mathematical expansion carried out to 8th order, which works out to roughly 80 separate parameters describing the surface. It also fits a scattering model, a description of how the rock reflects light at different angles, which is what allows the whole reconstruction to work across the enormous range of viewing geometries the observations covered. What came out the other side was 8 models. They are labelled A, A', a double prime, B, B prime, B double prime, C and C prime. 8 distinct best fit descriptions of how this asteroid is turning, each one produced by the same data, each one internally consistent. Now the number 8 is the one that has travelled. It is the number that shows up in coverage of this paper, and it is, in an important sense, misleading. So let me give you the more accurate version. The 8 collapse into 3 genuinely distinct families. Inside family A, the 3 variants differ only in the 3rd and 4th decimal place of the periods. The precession periods run 27.3743, 27.3737, and 27.3734. The rotation periods run 262.17, 262.12, and 262.08. The shape models they produce are, in the paper's own words, practically the same. They are not 3 answers. They are one answer with fuzz around it. The same holds for family B, clustered near 27.3633 hours of precession and 261.16 hours of rotation, and for family C, clustered near 27.3843 and 263.09. So the honour statement is not 8 competing answers. The honour statement is the one the authors themselves put in their conclusions. There are at least 3 statistically equivalent groups of solutions for Apophis's spin state at this moment. Statistically equivalent is a phrase that does a lot of quiet work, and it is worth pulling apart, because in ordinary speech it sounds like a hedge, and in this context it is not. It does not mean the team has a favourite and is being cautious. It does not mean one solution is somewhat more likely, and the others are long shots kept in the file for completeness. It means that when you take the observations, and you take the 3 families, and you ask which one the data prefers, the data does not answer. All 3 reproduce the measurements to within the noise. There is no statistical basis for choosing. If you picked family B over family A, you would not be making a worse choice. You would be making an unjustified one. If you want a concrete feel for what statistical equivalence looks like in practice, think about what the comparison actually involves. You take a model, you compute what brightness it predicts for every single one of the thousands of observations, and you compare that prediction to what was measured. The differences are the residuals. A good model leaves residuals that look like noise, scattered randomly with no pattern. A bad model leaves residuals with structure in them, a systematic drift, a repeating wave, something the model failed to capture. Family A, Family B, and Family C all leave residuals that look like noise. There is no pattern in any of them pointing to a better answer sitting nearby. The instrument has told you everything it can, and what it has told you is that 3 descriptions work. There is a second correction that needs making, and this one is where most public misreadings begin. These are not 8 competing pole directions. The direction the asteroid's angular momentum points is essentially the same across every one of the 8 models. That part is well determined, and everyone agrees on it. Apophis is not spinning one way in Family A and a completely different way in Family C. It is tumbling about the same axis in all of them. What differs between the families is not the direction of the motion. It is the number of turns. That distinction sounds technical and it is the entire story, so I will spend the next few minutes on it properly. But before I do, look at how small the differences actually are, because this is what makes the problem so unsettling. Family A puts the rotation period at 262.17 hours. Family B puts it at 261.16. That is a difference of about 1 hour out of 262, 0.4%. On the precession side, it is smaller still, 27.3743 hours against 27.3633, a difference of about 11 thousandths of an hour, 40 seconds, on a cycle that takes more than a day, 40 seconds. That is what separates the three futures. It is worth stating the full table, because seeing all 8 lined up is the fastest way to understand the structure. Family A runs at 27.3743, 27.3737, and 27.3734 hours of precession. Family B runs at 27.3633, 27.3637, and 27.3629. Family C runs at 27.3843 and 27.3851. Look at where the clustering happens. Within each family, the numbers agree to the 4th decimal place. Between families, they diverge at the 3rd. That is not a smear of uncertainty. That is 3 distinct islands with clear water between them. The moments of inertia move together with the periods, as they must. Family A sits around 0.6 for the first one. Family C sits closer to 0.63. Family B sits nearer 0.59. Slightly different mass distributions, each one paired with the rotation rate that makes it work. 3 self-consistent descriptions of the same object. You can measure the length of Apophis's wobble to 4 decimal places and still not know which of 3 answers is correct, and the wrong choice among them is a difference of 40 seconds in a 27-hour cycle. If somebody told you that a 40-second discrepancy in a day-long process was the thing standing between us, and a century of confident prediction, you would reasonably assume they were exaggerating. They are not, and the reason has nothing to do with the size of the difference. It has to do with what happens when you multiply a very small error by a very large number of repetitions and then hand the result to a planet. That is the initial condition. That is where the lever gets placed. Everything the encounter does to Apophis, and everything the asteroid does for the following 100 years, is a function of which of those 3 families is describing reality. And the honest position of the people who have studied it hardest, using the best dataset ever assembled, is that they do not know. So how do you lose count of something you have been watching for 22 years? Part 6. How you lose count of a turning rock. 8 years? That is the whole answer, and it is worth understanding exactly why. Apophis was observed well during the apparition that ran from December of 2012 to April of 2013. It was observed superbly during the apparition that ran from November of 2020 to May of 2021. In between those 2 windows there is a gap of roughly 8 years in which the asteroid could not be tracked with anything like the precision required. The reason is geometry, not neglect. An asteroid on an orbit like this one is only well placed for observation during particular stretches of its cycle. The rest of the time it is either too far away to be bright enough, or it is too close to the sun in the sky to observe safely, or both. For most of those 8 years, Apophis was doing exactly that. It was out there, turning, and nobody could count. Consider what an observer actually needs before a night is even possible. The asteroid has to be far enough from the sun in the sky that you can point a telescope at it after dark, which in practice means something above 60 degrees of separation. It has to be bright enough that a few minutes of exposure gives you a brightness measurement good to 1/100th of a magnitude, which for a 400-metre rock means it has to be reasonably close, and you need a run of clear nights, not one, because a single night of a 30-hour beat pattern tells you almost nothing. Those 3 conditions have to arrive together, and for an object on Apophis's orbit they only do so every several years. So now do the arithmetic on what happened during the gap. At a precession period of about 27.37 hours, over 8 years the asteroid completes approximately 2,560 precession cycles. At a rotation period of about 262 hours, it completes approximately 270 rotation cycles. The models have to assume a number for each. And here is the problem, stated as plainly as I can manage. The photometry fits equally well if you assume 1 more cycle of each, or 1 fewer. Family A is the nominal count. 2,560 precession cycles and 270 rotations. Family B assumes one more of each, so the asteroid must have been turning very slightly faster to fit them in. Family C assumes one fewer of each, so it must have been turning very slightly slower. All three then predict the 2020 and 2021 brightness data correctly, because all three arrive at the same orientation at the far end. There is a fingerprint that proves this is what is happening, and it is one of those details that turns a suspicion into a certainty. If the ambiguity really is a whole cycle miscount over an 8-year gap, then the competing solutions should not be scattered randomly through the parameter space. They should be spaced at a very particular interval, the interval you get by dividing the gap by the number of cycles and working out how much the period must shift to gain or lose exactly one. That is precisely what the search found. The local minima are separated by 0.0106 hours in precession period and by 0.969 hours in rotation period. Regular, repeating. Exactly the spacing predicted by a whole cycle miscount over that interval. The authors state the conclusion without softening it. Because the photometric data can be fitted about equally well with all three combinations of periods, they write, we cannot uniquely determine the number of cycles that elapse from 2013 to 2020. I want to press on the most important implication of this, because it is the thing that makes the problem hard rather than merely annoying. This is not a data quality problem. 67 nights of 100th magnitude photometry from a professional telescope in the Atacama, supplemented by more than 1,000 points from a space telescope, is not thin data. It is superb data, and more of it, taken now, would not fix this. You could point every large telescope on Earth at Apophis tonight and observe it perfectly for a year, and the 8 years between 2013 and 2021 would still be a hole. The information that was lost is not the kind you can recover by measuring harder later. It is the kind that had to be collected at the time. There is a version of this problem that engineers deal with constantly and have a name for. It is called phase unwrapping. Any time you measure something that cycles, and you sample it too infrequently, you cannot tell how many full cycles happened between your samples. It is the reason wagon wheels appear to spin backwards in old films. It is why radar altimeters and satellite interferometry have entire branches of mathematics devoted to resolving exactly this ambiguity. The mathematics is well developed. It just requires either denser sampling or an independent constraint, and for Apophis between 2013 and 2021 there was neither. The cleanest way I can put it is this. Imagine you photographed a clock face in 2013 and photographed it again in 2021. Both photographs are perfectly sharp. You can read both to the second, and you still have no way of knowing how many times the hand went round in between. The sharpness of your photographs is not the issue. Continuity is the issue, and you did not have it. That is the shape of the problem, and it is a shape this channel has run into before. The fireball story from the 15th of August was the same structure. The measured quantities, the trajectory and the energy, were reported with confidence and were solid. The quantity that actually determined where the object came from was a direction that nobody had gone back and checked. The failure was never in the measurement. It was in what got measured. For fairness, it is worth noting what earlier work said, because the ambiguity is not new so much as newly visible. An analysis published in 2014 put the precession period at 27.38 hours plus or minus 0.02 and the rotation period at 263 hours plus or minus 2. Look at those error bars against the three families. A window of plus or minus 2 hours on the rotation period swallows all three solutions whole. The earlier work was not wrong. It simply was not precise enough for the ambiguity to become apparent. The families only separate out once you get the precision down to the level where the gaps between them exceed the noise. There was also an analysis published in 2022 which reported formal uncertainties an order of magnitude tighter than the new work, and whose values fall outside the new intervals entirely. The Prague-led team addresses this directly. Those tighter error bars, they argue, correspond to confidence intervals calculated inside a single local minimum, rather than realistic uncertainties measured across the whole parameter space. In other words, if you search only in the neighbourhood of one solution, you will find that solution beautifully constrained, and you will never learn that two others exist. That is a specific and rather uncomfortable lesson about precision. A number can be reported to more decimal places than another number, and be less true, if the search that produced it was narrower. There is one further cruelty in the structure, and I am going to hold most of it for later, but it belongs here in outline. The three families do not stay separated forever. Because the mismatch between them is exactly one cycle over 8 years, they converge. Wait another 8 years and all three predict the same orientation again, and the ambiguity becomes invisible for a while before opening back up. The gap between the families is a thing that breathes. It widens and it closes and it widens again. Which means the question of when you look is not a matter of convenience. It is the whole game. So we have three families. We know why they exist. We know we cannot currently choose between them, which leaves the question that should be nagging at you by now. If all three families put the asteroid in nearly the same orientation in April of 2029, and they do, then why does it matter which one is right? Part 7. 20 degrees is not close enough. 20 degrees. That is the number that makes this whole problem look solved, and it is the number that makes it unsolvable. Here is the good news first, because it is real. When you take all three families of spin solutions and propagate them forward to April of 2029, they converge. They do not scatter. They do not diverge into wildly different predictions. All three put Apophis in approximately the same orientation when it arrives at Earth, agreeing to within about 20 degrees in the angles that describe the body's attitude. Break that down and it looks even better. The agreement is about 20 degrees in the precession angle, about 5 degrees in the nutation angle, and about 5 degrees in the rotation angle. Two of the three are pinned within 5 degrees. If you were skimming this paper, you would stop there. Three competing models that all agree on the answer to within 20 degrees sounds like a problem that has effectively solved itself. Take the middle one, note the uncertainty, move on. The paper does not let you do that. It says, in terms that leave no room for interpretation, that the post-encounter spin state is very sensitive to the exact orientation of Apophis, and that this accuracy is not sufficient to predict it precisely. And elsewhere, more bluntly still, the resulting effect of Earth's gravitational torque, they write, depends very sensitively on the exact phase of Apophis's rotation state at the moment of the closest encounter. So why is 20 degrees not good enough? The answer is in what a tidal torque actually is, and it repays a careful walk through. Earth's gravity does not pull on Apophis as though the asteroid were a point. It pulls harder on the near side than the far side, because the near side is closer. If the asteroid were a perfect sphere with its mass evenly distributed, that difference would stretch it slightly and do nothing else. But Apophis is not a sphere. It is an elongated, lumpy, two-lobed rubble pile whose long axis is substantially longer than its short one. For an elongated body, the difference in pull between the ends produces a twist. If the long axis is angled away from the line pointing at Earth, gravity tries to swing it back into line. That twist is the tidal torque, and its strength depends on two things: how close the body is, which falls off very steeply with distance, and what angle the long axis is presenting, which is a function of exactly where the asteroid is in its tumble at that instant. The distance dependence is savage. The gravitational pull itself falls off with the square of distance, but the tidal difference between the near side and the far side falls off with the cube. Double the distance and the twist drops to 1/8 of its former strength, which means that essentially all of the torque Apophis will ever receive from Earth gets delivered in the brief stretch when it is closest, and almost none of it in the long approach beforehand. The encounter is not a gradual application of force, it is a slap. Now add the crucial complication. The torque is not applied once. It is integrated over the entire approach, hour after hour, while the asteroid keeps tumbling through the whole encounter. So what matters is not one orientation. It is the sequence of orientations, the entire history of how the long axis swung through the approach. Change the starting phase by 20 degrees, and every moment of that history is different. The twist that was applied while the asteroid was pointed one way now gets applied while it is pointed another. Some of the contributions that would have cancelled now add. Some that would have added now cancel. And because these contributions accumulate over hours, small differences in the sequence produce large differences in the total. The timescale sharpens this further. All of the action, the entire transformation, occurs within about plus or minus 2 days, centered on the encounter, with the bulk of it concentrated into the hours around closest approach. This is not a slow squeeze applied over months. It is a hard, brief impulse, delivered while the asteroid happens to be facing one particular way. Try walking through it as a sequence. 24 hours out, Apophis is still nearly 200,000 kilometres away, and the twist it feels is negligible. 6 hours out, the distance has dropped enough that the torque is climbing steeply, and the asteroid has turned through perhaps a fifth of a precession cycle since the effect became measurable. In the final hour, the torque is at its maximum and changing fast, and the asteroid's long axis is swinging through a large angle while that maximum is being applied. Then it is passed, the distance opens back up, and within a day or so the twist has fallen back to nothing. The final state is the sum of everything that happened during that hour, weighted by which way the rock was pointing at each instant of it. Change the starting phase by 20 degrees, and you have not shifted the answer by 20 degrees. You have rerun the whole sequence with a different pairing between the peak of the torque and the swing of the body. That is why a modest input error does not produce a modest output error. There is a reason this feels familiar. It is a sensitive dependence on initial conditions, the property that sits underneath everything we call chaotic. Most people meet that idea in the abstract, as a butterfly in a hurricane, and it stays abstract because there is no butterfly you can point at. Here there is. The initial condition is a real orientation, of a real rock, on a real date, and the amplification factor is a planet. There is a tempting way out of this, and it does not work, and it is worth explaining why. The instinct is to average. If family A says one thing, family B another, and family C a third, take the middle and quote an uncertainty. That is a perfectly reasonable procedure for a linear system, where the output changes in proportion to the input. It fails completely for a nonlinear one. In a system this sensitive, the middle of three inputs does not give you the middle of three outputs. It gives you a fourth answer that no model produced and that has no claim to being right. So you cannot split the difference. You have to know which family is correct. There is a further consequence hiding in the sensitivity, and it is the one that will matter most when we get to the numbers. Remember that Apophis is tumbling in short axis mode, and that there is a second mode, long axis, with a boundary between them. That boundary is not a smooth gradient. It is a genuine dividing line in the physics, and a body sitting on one side of it moves in a qualitatively different way from a body on the other. The encounter pushes Apophis toward that line. How far it pushes depends on the same sensitive quantity we have been circling, which means the ambiguity in the starting state is not only an ambiguity about numbers, it carries a small but real ambiguity about what kind of motion this asteroid will be doing afterwards. A reasonable question at this point is why nobody simply sent something out to measure it years ago and settled the matter. The answer is timing and money. Apophis was a moderately interesting rock on a long list of moderately interesting rocks until the 2029 encounter became the organizing fact of its scientific life. Missions take a decade to plan and build. The window in which anyone was motivated enough to fund a dedicated Apophis spacecraft opened, realistically, after the encounter geometry was well understood, and by then the launch dates that remained were the ones that get you there in 2029 and not before. We have always assumed that the hard part of tracking an asteroid is knowing where it will be. That is the intuition every space movie has drilled into us, and it is the intuition behind the entire public conversation about planetary defense. But what if the position was never the difficult question? What if the difficult question was which way the thing is facing? For Apophis, that is exactly where we have ended up. The trajectory is one of the best determined in the catalogue. The orientation, going into the most consequential few hours in this object's recorded history, is known to 20 degrees. The encounter is a lever, and 20 degrees is how precisely we know where the lever is set, which means the only thing left to establish is how much the lever actually moves. What does come out the other side? Part 8. The thousandfold widening. To find out, the team did the only thing you can do with a system this sensitive. They ran it 1,000 times. The procedure is called a bootstrap. You take your best fit model, and instead of propagating that single solution forward, you generate 1,000 slight variants of it, each one drawn from within the range the data allows. Then you push all 1,000 of them through the encounter, using the full physics, starting from a fixed epoch at the beginning of 2021 and running well past September of 2029, months after the pass. What comes out is not a prediction, it is a distribution, a cloud of possible futures, and the width of that cloud is the answer to how well we can predict this object. For this first set of runs, the physics included gravity and nothing else. No sunlight, no thermal effects, just Earth, Apophis, and the twist between them. That restriction matters, and we will come back to it. because leaving out the other force turns out to be the largest assumption in the whole exercise. Here is what the cloud looked like. The precession period goes in at 27.374 hours, known to 1,000th of an hour. It comes out somewhere between 24.5 and 27.5 hours, with the median of the 1,000 runs sitting near 25.75. Read those two ranges against each other. Going in, the uncertainty is measured in thousandths of an hour. Coming out, it is measured in whole hours. The window is 3 hours wide, where it used to be a rounding error. The rotation period goes in at 262.2 hours, known to 1/10. It comes out somewhere between 230 and 290 hours, roughly centered on where it started. That is a 60-hour window. 2.5 days of uncertainty on a quantity that we currently know to within 6 minutes. Stated as a single number, the uncertainty in both periods expands by more than a factor of 1,000. There is a detail in how those 1,000 runs were displayed that I find quietly devastating. The authors colour-coded them by which family each starting variant came from. Family A in blue, Family B in red, Family C in green. If the three families led to three separable futures, you would see three distinct clusters, and you could at least say that whichever family turns out to be correct, here is the corresponding prediction. That is not what the plots show. The three colours are interleaved. The families do not sort into tidy outcomes. They spray across the same range, overlapping, because the sensitivity is severe enough that variants within a single family end up further apart than variants from different families. So you cannot even use the ambiguity constructively. There is no version of this where you say, if it turns out to be family B, then the answer is this. The uncertainty is not three options. It is a fog. I want to make sure that lands correctly, because it is easy to hear it as a statement about the asteroid becoming unpredictable in some general sense. It is more specific and more interesting than that. The trajectory of Apophis through the encounter remains superbly known. We are not losing track of where it goes. What we are losing is the ability to say how it turns, and because the turning governs the sunlight-driven drift, we eventually lose some of the ability to say where it goes as well, decades later, by a slower route. I want to make sure that lands correctly, because it is easy to hear it as a statement about the asteroid becoming unpredictable, in some general sense. It is more specific and more interesting than that. The trajectory of Apophis through the encounter remains superbly known. We are not losing track of where it goes. What we are losing is the ability to say how it turns, and because the turning governs the sunlight-driven drift, we eventually lose some of the ability to say where it goes as well, decades later, by a slower route. There is a practical consequence to this that hits within weeks of the encounter itself. A spacecraft arriving at Apophis in the summer of 2029 has to know how to point at it, how to plan an orbit around it, and when its cameras will see which parts of the surface. All of that requires a working spin model. If the post-encounter periods are only known to within tens of hours, that mission planning becomes a scramble carried out on the fly, with new observations feeding a rebuilt model while the spacecraft is already there. It is doable. It is also a great deal harder than arriving with a model you trust. The physical picture underneath the numbers is worth reconstructing, because it explains why the answer is a cloud rather than a value. The asteroid approaches on a hyperbolic path. For weeks beforehand, Earth is a bright dot and nothing measurable happens to the tumble. In the final day, the tidal torque climbs steeply as the cube of the shrinking distance. Around 21:46 Universal Time on the 13th of April it peaks, and while it is peaking, the asteroid keeps rotating through its own motion, presenting a changing profile to the planet the entire time. Then the geometry opens back out, the torque collapses, and Apophis carries away whatever new state it happens to have ended up in. All of the action, in the author's description, occurs within about plus or minus 2 days centered on the encounter. Everything before that is approach, everything after is consequence, and because the body is rigid through the whole thing, none of that energy goes into deforming it. There is no crumpling, no settling, no internal friction bleeding the impulse away. The entire effect shows up as a change in how the asteroid turns. It is a remarkably clean experiment if you happen to have measured the starting conditions. Then there is the question of mode, which is the part I find genuinely unsettling. Recall that Apophis tumbles in short axis mode and that a second mode exists, long axis, with a boundary between them. In the technical language, the boundary is a separatrix, which is a fancy word for a genuine dividing line in the behavior of a system. Bodies on one side of it move one way, bodies on the other side move a qualitatively different way. It is not a gradient, it is a switch. Whether a body is on one side or the other is decided by a single dimensionless number that combines its rotational energy, its angular momentum, and how its mass is distributed. Below a certain value, short axis mode. Above it, long axis. The number crossing that threshold is not a gradual transition into a slightly different behavior. It is the point at which the axis stops circulating around one dimension of the body and starts circulating around another. For an observer on the surface, if there were one, the sky would reorganize itself. In all 1,000 gravity-only runs, Apophis stayed on the short axis side, every single one, but the distribution moved. The authors note that the mean effect of Earth's gravitational torque shifts the rotation state toward the separatrix. The asteroid does not cross the line, but the whole cloud of outcomes slides closer to it than it was before, which is why the phrasing in the conclusions is what it is. The short axis spin mode, they write, will be preserved with a high likelihood. Not certainly, with a high likelihood. That is a carefully chosen sentence from people who ran the simulation and watched their outcomes drift toward a boundary they could not entirely rule out crossing. One more feature of those results deserves attention because it tells you something about the direction the encounter pushes. The precession period does not scatter symmetrically, it shortens. The median comes out at about 25.75 hours against a starting value of 27.37, and the whole range sits below the current figure rather than straddling it. The rotation period, by contrast, stays roughly centered on where it began, so the wobble speeds up while the underlying turn stays about the same. That is a real asymmetry in the physics rather than an artifact of the sampling, and it means whatever Apophis is doing after 2029, it is doing it with a faster wobble than it has today. So this is where the gravity-only picture leaves us. An asteroid whose rotational description is about to be rewritten in an afternoon, whose new periods will be known to within hours rather than seconds, and whose fundamental mode of tumbling is very probably preserved but has moved measurably closer to changing, and one of the outputs of those simulations changes by more than 100 degrees. Except that it does not, and the reason why is one of the more elegant misdirections in this entire subject. Part 9. The pole that moves 100 degrees, and also 10. 100 degrees. That is the number sitting in the output of the simulations, and read carelessly it says that Earth flips this asteroid over. Specifically, the ecliptic longitude of Apophis's rotational angular momentum vector changes by more than 100 degrees during the encounter. Longitude in this coordinate system is the direction the pole points measured around the plane of the solar system. A shift of 100 degrees in that quantity would ordinarily mean an enormous reorientation. It does not mean that here, and the reason is entirely geometric, go back to where the pole sits, ecliptic latitude minus 87.2 degrees. That is within 3 degrees of pointing straight at the south pole of the solar system's plane. Now think about what longitude means when you're standing next to a pole. If you are on the equator, walking 100 kilometres east changes your longitude by about 1 degree. If you're standing 3 meters from the geographic North Pole, walking a few paces around it takes you through every line of longitude on the planet. You have travelled almost nowhere and your longitude has gone all the way round. Apophis's angular momentum vector is standing 3 degrees from the pole, so when the encounter tips it, the longitude reading swings wildly and the actual physical reorientation is small. Here is the real number. The true median tilt of the angular momentum vector across those 1,000 simulations is about 9.8 degrees. There is a second reason the pole sits where it does that is worth a moment, because it is not an accident. A tumbling body under a long history of thermal torques tends to have its angular momentum driven toward particular orientations, and near polar is one of the attractors. So Apophis, pointing almost straight out of the plane of the planets, is itself a clue about how long these forces have been working on it, and how strongly. The very geometry that makes the longitude reading misleading is also a record of the physics that produced it. The authors are explicit about the distinction, and the fact that they went out of their way to be explicit tells you they anticipated exactly the misreading I am describing. More than 100-degree change in pole longitude during the Earth encounter, they write, appears dramatically large, but most of the effect is apparent. Due to near polar latitude, the real tilt is much smaller. To make the geometry concrete, picture the angular momentum vector as a pencil standing almost upright, leaning 3 degrees off vertical. The encounter knocks it. It is now leaning about 10 degrees off vertical instead. The tip of the pencil has moved a small distance, but the direction it leans, measured as a compass bearing, has swung right around because when something is nearly upright, its lean has almost no preferred direction, and a small nudge can send it anywhere. The bearing changed by 100 degrees. The pencil moved a few degrees. Both statements are true, and only one of them is about physics. There is a related quantity that matters more for what comes next, and it is smaller still. The obliquity, defined here as the angle between the asteroid's angular momentum and the normal to its orbit, changes by a median of about 5.7 degrees. That is the one to remember, because obliquity is the number that feeds into the sunlight-driven drift. Everything in the next few minutes runs through it. Obliquity is the same quantity that gives Earth its seasons, the tilt between how a body spins and how it orbits. On our planet, it sits at about 23.5 degrees, and it governs the entire climate. On Apophis, it governs which hemisphere gets baked and which stays cold, which sets where the thermal push points, which sets where the asteroid goes. The timing of that change is worth noting as well, because it is abrupt in a way that is hard to overstate. Plotted against time, the tilt sits flat for months, then moves almost vertically over the space of about 2 days, then goes flat again at a new value. There is no run-up and no settling. The asteroid has one orientation for its entire recorded history, and then a different one, and the transition happens over a weekend. Now, none of this should be taken as an argument that the effect is trivial. 10 degrees of tilt on a body that was already tumbling in a complicated 2-period motion is a real reorientation. It changes which parts of the asteroid see the sun, and for how long. It changes the thermal cycle across the surface. On a body where the surface material is already sitting at the edge of stability, a 10-degree change in the effective gravity field is exactly the sort of thing that redraws the slope map we talked about earlier. It is a genuine and consequential change. It just is not a flip. I am spending time on this for a reason that goes beyond accuracy. The 100-degree figure is precisely the kind of number that gets extracted from a technical paper, stripped of its context, and turned into a headline about an asteroid being flipped over by Earth's gravity. And once that headline exists, the correction never catches up with it. The people who wrote the paper knew that, which is why the clarification sits right there in the caption of the figure, in plain language, where nobody who reads the paper can miss it. There is one more thing to say about that 9.8-degree figure, and it is the reason we are here. It is a median. Across the 1,000 runs, the tilt is not always 9.8 degrees. It is scattered, and the width of that scatter is inherited directly from how well the starting orientation was known, which is to say, the spread on the answer is a measurement of our own ignorance rather than a property of the asteroid. That distinction is one of the more useful ideas to carry away from any of this. There are 2 kinds of uncertainty in a prediction. There is the kind that comes from the system genuinely being random, which no amount of measurement will remove. And there is the kind that comes from you not having measured something you could have measured. They look identical in the output. They are completely different in what you can do about them. Almost all of the width in these Apophis predictions is the second kind. It is not that the universe has not decided, it is that we did not look. There is a habit of mind buried in this section that is worth taking with you, because it applies far beyond asteroids. When a quantity in a scientific result looks enormous, the first question is not whether it is true. It is what coordinate system it was measured in. Longitude near a pole, percentage change on a tiny baseline, ratios where the denominator is nearly 0. These all produce numbers that are technically correct and physically misleading. The 100-degree pole shift is the textbook case. It is in the data. It is in the paper. It means almost nothing. A 10-degree tilt on a 400-meter rock sounds like a footnote in a technical appendix. It is about to move this asteroid through space. Part 10. Sunlight as a steering force. Stand a rock in sunlight and it warms up. Turn the rock, and the warm part goes into shadow, and it keeps radiating that heat away for a while afterwards, because heat takes time to leave. That is the entire mechanism. Everything else is bookkeeping. An asteroid absorbs sunlight on its day side. it remits that energy as infrared radiation, but it does not re-emit it instantly, and it does not re-emit it evenly. The surface has thermal inertia, so the warmest point is not the spot directly under the sun. It is a spot that has rotated some way past noon, the same reason the hottest part of a summer day is mid-afternoon rather than midday. And radiation carries momentum, so the afternoon side of the asteroid pushes slightly harder than the morning side. The result is a net force, permanently applied, pointing in a direction determined by which way the body is spinning. It is called the Yarkovsky effect, after a Polish civil engineer who worked it out around the turn of the 20th century and published it in a pamphlet that was very nearly lost entirely. For most of the following century it was regarded as a theoretical curiosity, on the reasonable grounds that a force this feeble could not possibly matter. The force is genuinely feeble. We are talking about a push measured in fractions of a newton, acting on an object with a mass in the tens of billions of kilograms. If you sat on Apophis with a stopwatch, you would never detect it. Over a human lifetime, it is nothing. Over decades, it moves the orbit. Over millions of years, it is one of the main reasons asteroids get delivered from the main belt into the inner solar system at all. Sunlight integrated over long enough is a transport mechanism for rocks. There are two flavours of it, which is worth knowing because they push in opposite directions. The daily version comes from the day-night cycle as the body rotates, and depending on which way the body spins, it either pushes the asteroid outward from the sun or drags it inward. The seasonal version comes from the annual heating cycle as different hemispheres are tilted toward the sun over an orbit, and it always drags inward. Which one dominates depends on the rotation rate, the obliquity, and the surface properties. Untangling them for a specific object is exactly the kind of work that requires knowing the spin state. For Apophis, the effect is not theoretical. It has been measured, and measured extraordinarily well. The detection of Yarkovsky acceleration on Apophis is described as the second most precise ever achieved, behind only Bennu, which had a spacecraft parked next to it for years. The current determination is accurate to about 0.5%. It is worth understanding how you measure a force that's small on an object you have never touched. You do not measure the force. You measure where the asteroid is, over and over, for 22 years, using optical positions and radar ranging. Then you compute where pure gravity says it should be, accounting for the Sun, all the planets, and the larger asteroids. Then you look at the difference. If the object is consistently a little ahead of or behind where gravity alone puts it, and the discrepancy grows in the particular way a thermal push would produce, you have detected Yarkovsky. It is an inference from an accumulated positional discrepancy, which is why it takes decades and why it gets dramatically better every time somebody adds a radar measurement. That number is the reason the orbit is so well known, and it is the number the encounter is about to change. Follow the chain carefully, because this is the spine of the whole story. First link. The obliquity changes by a median of about 5.7 degrees. Obliquity controls the geometry of the thermal push, because it sets how the day-night cycle is oriented relative to the direction of travel. The authors estimate that this change alone alters the Yarkovsky acceleration by about 0.9%. Hold that against the current measurement precision of 0.5%. The obliquity change by itself is already larger than the accuracy we have. The effect has moved further than our ability to see it. Second link, and this one is bigger. The dominant contribution to the post-encounter drift is not the obliquity at all. It is the change in the semi-major axis. Remember that the encounter lifts Apophis from an Atene orbit to an Apollo orbit. A larger orbit means a different distance from the Sun, a different amount of absorbed sunlight, a different surface temperature, and therefore a different push. Third link. The rotation period changes too, and the rate of spin controls how far the heat gets carried around the body before it is radiated. That is a genuinely separate contribution. Now here is where the paper does something that I think is worth pausing on, because it is a small act of scientific housekeeping that most coverage will skip entirely. An earlier published treatment of this problem used a scaling relation to estimate the post-encounter drift, treating it as proportional to the semi-major axis raised to the power of -0.5, multiplied by the cosine of the obliquity. Clean, simple, and the sort of expression that gets reused because it is easy. The Prague-led team states plainly that this scaling is not correct. The reason is that it omits the thermal parameter. The thermal parameter is a measure of how efficiently heat gets carried around a rotating body before it escapes. If a surface conducts heat poorly and the body spins fast, heat barely moves, and the parameter is small. If the surface conducts well or the body turns slowly, heat gets carried a long way around and the parameter is larger. It sets the character of the whole effect, and crucially, the way the drift rate depends on everything else changes depending on which regime you are in. Apophis, with its very slow 11-day rotation and a hot subsolar point, sits in a regime where the drift rate scales with the thermal parameter rather than against it. So an increase in orbital distance and a slight decrease in the precession period both push the drift rate up rather than down. The old scaling had the sign of part of the effect backwards. The size of that thermal parameter depends on how well the surface conducts heat, and that is itself uncertain. Taking a value near the upper end of what has been reported for bodies of this type, from thermal infrared observations and from the spacecraft that have visited similar asteroids, puts Apophis's thermal parameter at around 1/2, comfortably in the regime where the scaling runs the way the new analysis says it does, and not in the regime the old expression assumed. That is a small piece of housekeeping in a technical paper. It is also, in a specific and unglamorous way, exactly what science is. A group looked at a convenient formula that other people had been using, checked whether the assumptions behind it applied to this particular object, found that they did not, and said so in print. Working it through correctly, the expectation is roughly a 20% increase in the Yarkovsky drift rate after the encounter. Now assemble the full chain and look at it as one object. The spin state determines the obliquity and the rotation period. The obliquity and rotation period, together with the new orbit, determine the thermal parameter. The thermal parameter determines the Yarkovsky drift. The Yarkovsky drift determines, over decades and centuries, where this asteroid actually is. Every statement anyone makes about where Apophis will be in the year 2100 travels down that chain, and the first link in it is the one that currently has 3 answers. There is a scale on which this stops being about one rock. This is how the solar system quietly rearranges its small bodies, not primarily by collisions, which are rare and spectacular, but by sunlight, applied without pause for millions of years, nudging rubble piles out of stable orbits and into ones that cross the paths of planets. Apophis is on an Earth-crossing orbit today because this force has been acting on it, and on whatever it broke off from for a very long time. In 2029, we get to watch the steering change in real time on a rock we can see with the naked eye. And there is a second force in this system that has never been measured at all. Part 11. The torque nobody has measured. Every number in the last 2 parts came from a model that deliberately left something out. The 1,000 simulations, the 24.5 to 27.5 hour window, the 9.8 degree tilt, all of it was computed with gravity alone. Not because the missing force is small, because nobody knows how big it is. The missing force is the rotational sibling of the Yarkovsky effect, and it goes by an acronym assembled from the surnames of 4 researchers who contributed to the theory. In practice, everybody just calls it YORP. The physics is the same thermal re-emission we just walked through. The difference is what it acts on. Yarkovsky produces a net push on the body's centre of mass, which changes the orbit. YORP produces a net twist, which changes the spin. And it only exists because asteroids are lumpy. On a perfect sphere, the thermal pushes from every facet cancel out and there is no torque. On an irregular body, they do not cancel, and the leftover is a torque that has been applied continuously for as long as the object has existed. The effect is what spins some small asteroids up until they shed material, and what slows others to a near stop over millions of years. It is one of the dominant forces shaping how small bodies rotate. Its fingerprints are all over the small body population once you know to look for them. A large fraction of near-Earth asteroids of a few hundred meters have a distinctive shape, wider at the equator than at the poles, like a spinning top or a child's toy. That shape is what happens when a rubble pile is spun up gradually, until loose material migrates toward the equator and piles up there. Bennu has it, Ryugu has it. Both were visited by spacecraft, and both showed exactly the equatorial ridge the theory predicted. There is also a population of small binary asteroids, rocks with a moon of their own, and the leading explanation for how they form is that the parent was spun fast enough to shed a piece that stayed in orbit. Sunlight doing that, over millions of years. So this is not a marginal effect that we are including for completeness. On bodies of this size, over these timescales, It is one of the main things going on. For Apophis, it has never been measured. Not once. Its magnitude is unconstrained. So the team did the only honest thing available, which was to estimate it by analogy and see what happened. The natural comparison is Itokawa, an asteroid of similar size and similar stony composition that was visited by a Japanese spacecraft and has been watched closely enough that its Yorp-driven acceleration has actually been observed. The measured value there is about 4 times 10 to the minus 8 radians per day squared. That number is so small it is hard to hold on to. It is an acceleration of a rotation rate, and it is tiny. But it accumulates as the square of time, which means the longer you wait, the faster the effect grows. Apply something comparable to Apophis. Over the roughly 17 years between the 2012 observations and the 2029 encounter, and the accumulated contribution is about 45 degrees of rotation phase. 45 degrees. Set that against everything we established earlier. The 3 families of spin solutions agree with each other on the 2029 orientation to within 20 degrees, and we spent a long time establishing that 20 degrees is already too coarse to give a reliable prediction. The unmeasured force could be contributing more than twice that. The authors do not soften it. Such a value, they write, would hugely change the prediction of the spin change during the 2029 encounter, and then they add the sentence that closes off the last escape route. Even a few times smaller effect would still be relevant. So they ran the simulations again, this time including an estimated Yorp torque at a moderate assumed strength, and the results are worth putting directly alongside the gravity-only numbers. Gravity alone, the post-encounter precession period lands between 24.5 and 27.5 hours. With Yorp included, it lands between 16 and 35 hours. Gravity alone, the rotation period lands between 230 and 290 hours. With Yorp included, it lands between 160 and 400. Look at what happened to those windows. The precession range went from 3 hours wide to 19 hours wide. The rotation range went from 60 hours to 240. The uncertainty introduced by one unmeasured term is several times larger than the entire uncertainty from the known physics. The missing variable is not a correction, it is most of the answer, and that was at a moderate assumed strength. The simulations included a scaling factor to account for the fact that nobody knows the real magnitude, and the runs I just described used a value of about 4/10. When the team pushed that factor to 7/10 or above, something new appeared in the results. A small fraction of the outcomes crossed the separatrix. Under a stronger assumed torque, some versions of Apophis come out of the encounter tumbling in long-axis mode instead of short-axis mode. Not most of them, a minority. But it went from impossible to possible purely by changing a number nobody has measured. That is the state of the prediction. Whether this asteroid emerges from April 2029 tumbling the same fundamental way it went in depends on the strength of a force we have never observed acting on it. The acronym itself is a small monument to how these things get named. It carries the initials of 4 researchers who each contributed a piece of the theory across most of a century, from the same Polish engineer who worked out the orbital version, through an American geophysicist, a Russian astronomer, and an American aerospace scientist who noticed the same effect while thinking about something else entirely. Nobody sat down and discovered it. It accreted. There is a specific reason Yorp is hard here, and it is the tumbling. On a body rotating cleanly about one axis, you can work out the torque with a manageable calculation. On a tumbler, every facet of the surface is presented to the sun, in a constantly shifting pattern that never repeats the same way twice, and the whole thing has to be done numerically. Tumbling does not prevent Yorp from operating. It just makes modelling it considerably harder, which is part of why nobody has pinned it down. And there is a strong argument that it is definitely there, which the paper makes in one line. Yarkovsky and Yorp are the same physics acting on 2 different quantities. Yarkovsky has been detected on Apophis to 0.5%, one of the best measurements of its kind ever made. If the thermal re-emission is unambiguously pushing the orbit, then it is unambiguously twisting the body as well. We know the torque exists, we simply have no idea of its size. There is a way to see this as good news, and I think it is the fairer reading. An unmeasured quantity is a solvable problem. If the dominant uncertainty in the 2029 prediction was something fundamental about the nature of the encounter, there would be nothing to do about it. But it is not. It is a torque that has a definite value right now acting on a real object, and that value would show up in a long enough baseline of brightness measurements as a systematic drift that none of the fixed period models can absorb, The same observing campaign that would settle which family is correct would also constrain this. 1 program, 2 answers, so the tally now stands at 2 unknowns rather than 1. We do not know which of 3 families describes how Apophis is turning, and we do not know how hard sunlight has been twisting it for the last 17 years. Both of those have the same solution, and both of them have the same deadline. How much time is actually left? Part 12. Keyholes and what ruled out. Actually rests on. On the 27th of December, 2004, an asteroid discovered 6 months earlier was assigned a rating that no object has ever received before or since. To understand why Apophis carries the emotional weight it does, you have to go back to that week, because everything the public believes about this rock was formed then and has never quite been updated. It was found on the 19th of June, 2004, at Kitt Peak National Observatory outside Tucson, Arizona, by 3 astronomers named Roy Tucker, David Tholen and Fabrizio Bernardi. It was lost almost immediately, as newly found asteroids often are, and recovered again in December by a survey in Australia. And once there were enough positions to fit an orbit, the fit came back with something alarming in it. The computed probability of Apophis striking Earth in 2029 climbed through the following days: 1 in 300, 1 in 200, 1 in 62. At its peak it reached about 2.7%. 2.7% is not a large number in ordinary life. It is an enormous number for an asteroid impact. It is roughly the odds of drawing a specific card from a shortened deck applied to a 340-metre rock hitting a planet with people on it. There is a scale for this, called the Torino Impact Hazard Scale, running from 0 to 10, designed to communicate risk to the public without requiring anybody to interpret probabilities. Most objects that ever get non-zero ratings sit at 1, meaning a routine discovery that merits attention and will almost certainly be downgraded. Apophis was assigned a 4. That means a close encounter with a 1% or greater chance of a regionally devastating collision. Nothing else has ever been rated 4, not before, not since. Apophis holds that record alone, and it held it for about 4 days. What ended it was not a new observation, it was an old one. Astronomers went back through archival images taken before the discovery, found Apophis sitting in plates from earlier that year where nobody had known to look, and added those positions to the orbit fit. With a longer arc of observations, the solution tightened, and the 2029 impact case vanished entirely. But the 2029 case vanishing did not close the story, and the reason is a concept that has shaped every serious discussion of this asteroid for 20 years. The concept is the gravitational keyhole, and I want to take it slowly because it is simultaneously the most important and the most misunderstood idea in this whole subject. When Apophis passes Earth in 2029, its new orbit depends on exactly where it passes. Pass a little further out and Earth's gravity bends it a little less. Pass a little closer and it bends more. Every possible approach distance produces a slightly different outgoing orbit, and therefore a slightly different orbital period around the Sun. Now, most of those outgoing orbits never bring the asteroid back to a dangerous place, but a small number of them do something very specific. They set the new orbital period to an exact ratio with Earth's year. 7 of the asteroid's orbits in exactly 6 of ours, for example. And when the periods lock into a whole number ratio like that, the asteroid returns to the same point in space at the same time as Earth does, on a schedule, years later. The region on the encounter plane that produces one of those resonant orbits is called a keyhole. Pass through it, and the 2029 encounter has aimed the asteroid at a future collision. Here is the number that makes it vivid. The keyhole corresponding to an impact in 2036 is on the order of 800 meters wide. 800 meters, a target the size of a few city blocks floating in space, in a pass that takes place 38,000 kilometres from the centre of the Earth. The odds of threading it are exactly as small as that sounds, which is the point. But the existence of it is why nobody could simply declare the matter closed in 2005. The definitive work on those keyholes came from a team at NASA's Jet Propulsion Laboratory, led by a researcher named David Farnocchia, published in the journal Icarus in 2013. What they did is directly relevant to everything we have been discussing, because they ran into the same wall. To know where Apophis will pass in 2029, you need to know how the Yarkovsky effect will move it between now and then. To know that, you need to know the spin orientation. And in 2013, the spin orientation was not known. So they did the honest thing. They ran a Monte Carlo simulation across the full range of possible spin orientations, propagated all of them forward, and mapped the resulting cloud of possible arrival points onto the encounter plane. Then they checked which keyholes that cloud overlapped. Their answer was that the probability of hitting the 2036 keyhole was about 1 in a billion, and the probability of hitting the 2068 keyhole was about 1 in a million. 1 in a million is very small. It is also not zero, and for an object of this size, 1 in a million is above the threshold at which planetary defense people keep watching. What closed it was radar. In March of 2021, with Apophis about 17 million kilometres from Earth, the Goldstone antenna in California transmitted at the Asteroid, and the Greenbank telescope in West Virginia received the returning signal. Radar has a property that optical astronomy does not. It measures distance directly, by timing the round trip of the pulse, rather than inferring distance from angular position over long baselines. A single good radar range can be worth years of optical astrometry for pinning down an orbit. Those observations tightened the solution enough that the 2068 keyhole fell outside the range of possible arrival points. That is where the current statement comes from. No impact risk for at least the next 100 years. Now, I want to handle something directly, because it circulates constantly, and because it deserves an honest answer rather than dismissal. There is a persistent line of thinking that says the 2029 pass is the setup, that the real event is later, and that the reassurance about 100 years is a managed message. And I understand entirely why that idea has traction, because unlike most claims of that shape, this one has a real historical root. The keyholes were genuine. The Torino 4 rating was genuine. The 2068 case was genuinely open in the peer-reviewed literature until 2021. Nobody made that up. What closed it, though, is the hardest kind of evidence to argue with. Radar ranging is a direct physical measurement of distance, performed by two separate facilities, on a target that anybody with a large enough dish could have independently observed at the same time. It is not a model, it is not a simulation, it is a timed pulse. There is a related claim that has appeared more recently, and it is a misreading of the very paper this whole video is about. It says that because there are now 8 competing models of Apophis, scientists do not actually know whether it will hit us. That conflates two entirely separate quantities, and once you see the confusion, it cannot be unseen. The orbit of Apophis, the path it takes through space, is among the best determined in the entire near-Earth catalogue. The thermal drift on it has been measured to 0.5%, the second most precise such measurement ever made. What has 8 models is the rotation, the tumble, which way the rock is facing. You can know exactly where a spinning top will be on the table, without knowing which way its handle will be pointing when it gets there. Those are different questions, answered by different instruments, and being uncertain about one says nothing whatsoever about the other, and the suggestion that this is being concealed runs directly into the paper itself. 20-plus authors across 11 countries published in the open literature, a result whose headline finding is that they do not yet know something well enough. They corrected another group's published scaling relation in print. They flagged their own formal error bars as optimistic, and they finished by asking amateur astronomers for help. Institutional concealment does not usually look like a public appeal for more telescope time. But here is the part that most coverage leaves out, and it is the reason the keyhole story belongs in this video at all rather than in a history segment. No impact risk this century is a real and well-supported conclusion. It is also a statement whose long tail rests on the Yarkovsky drift rate. And the Yarkovsky drift rate is the exact quantity that the 2029 encounter is about to change by roughly 20%, in a direction and magnitude that cannot be fully computed until somebody measures the post-encounter spin state. The authors say as much themselves, in the flattest possible language. The possibility of constraining Apophis's post-encounter state after April 2029, they write, important among other topics for its future orbital evolution, including analysis of the Earth impact hazard, is the primary motivation for a unique and accurate pre-encounter model of its spin state. That sentence is the whole video in one line. The reason the spin state matters is that it feeds the drift, and the drift feeds the hazard analysis. The keyhole framework is not history. It is the reason anybody funded this work. So the next question is obvious. Who is going to be there to make the measurement? Part 13. The Witnesses. In an industrial building in Italy, engineers are currently assembling a spacecraft that has to launch on time or not at all. The mission is called RAMSES, which stands for Rapid Apophis Mission for Space Safety, and the word rapid is doing real work in that name. Most planetary missions are built over a decade or more, with schedule margin measured in years, because if you miss a launch window the target comes round again. Apophis does not come round again. The encounter happens on the 13th of April 2029 whether or not anybody is ready. The European Space Agency committed to the mission in full at its Ministerial Council meeting in November of 2025. On the 10th of February 2026, it signed a contract worth €81.2 million with OHB Italia to build, assemble and test the spacecraft. That contract begins the construction phase, followed by environmental and functional testing, aiming at a launch window in the spring of 2028. The launch itself will be Japanese. On the 7th of May 2026 in Berlin, the European Space Agency and the Japan Aerospace Exploration Agency signed two agreements, a Memorandum of Cooperation on Planetary Defense and a dedicated partnership deal for RAMSES specifically. The spacecraft will fly on a Japanese H-3 rocket, currently targeted for April of 2028, and then the number that matters more than any of the others. RAMSES arrives at Apophis in February of 2029, 2 months before the encounter. That timing is the entire point of the mission, and it is worth being clear about why. A spacecraft that arrives afterwards can tell you what state the asteroid ended up in. Only a spacecraft that arrives beforehand can tell you what state it started in. RAMSES is being built, at speed, to be the before photograph. The American contribution comes at the other end. OSIRIS-APEX is not a new spacecraft. It is the former OSIRIS-REx, the mission that flew to the asteroid Bennu, collected a sample, and dropped that sample through Earth's atmosphere in a capsule in September of 2023. With the primary mission complete and the spacecraft still healthy, NASA redirected it. New target, new name, same hardware. Getting from a Bennu return trajectory to an Apophis rendezvous is not simple, and the route has been brutal on the vehicle. It requires 6 close passes of the Sun and 3 gravity assists off Earth. Those solar passes take the spacecraft to within about 46.5 million miles of the Sun, between the orbits of Mercury and Venus, roughly 25 million miles closer than anything in its design specification allowed for. Engineers handled it by locking the spacecraft into a fixed orientation relative to the Sun and repositioning one of its 2 solar arrays to throw shade across the most heat-sensitive components. It survived the second of those passes, and a review completed in January of 2025 confirmed no surprises in any of the data. OSIRIS-APEX arrives in late June of 2029 after the encounter, and then stays. The plan includes a maneuver in which the spacecraft descends close to the surface and fires its thrusters at the ground to blow away the top layer of regolith, exposing what is underneath for its instruments to look at. Given everything we discussed about fresh material and space weathering, that is a well-chosen experiment. There is something worth noticing in that arrangement, which is how much of it is improvised. OSIRIS-APEX exists because a spacecraft happened to still be working after its mission ended, and somebody asked where else it could go. RAMSES exists because a European planetary defense program was able to move faster than its own normal timelines allow. Destiny. Plus was designed for a different target entirely. None of this was planned 20 years ago as a coordinated response to the 2029 encounter. It was assembled in a hurry out of hardware and programs that were mostly built for other reasons because the date is fixed and there was no time to do it properly. A third spacecraft, the Japanese Destiny Plus mission, is planned to fly past Apophis in February of 2029 as well. It is worth pausing on what a 2-month lead time really buys, because it is less than it sounds. RAMSES arriving in February means roughly 60 days of proximity operations before the encounter. In that time, it can image the shape at resolutions no telescope will ever achieve, measure the surface thermal properties directly, and watch the rotation from close range. All of that is enormously valuable, but 60 days is a little over 2 rotation periods, 2 turns. You cannot resolve a period ambiguity that hinges on counting cycles across 8 years by watching 2 of them, no matter how good your camera is. What the spacecraft can do is anchor the model. It can measure the shape and the mass distribution well enough that the moments of inertia stop being fitted parameters and start being measured ones, and that alone would narrow the search considerably. But it works alongside the ground-based photometry rather than replacing it. The 2 measurements answer different halves of the question. So there will be a European spacecraft on station before, a Japanese flyby before, and an American spacecraft on station after. A before and after dataset on a small body being physically altered by a planet. Nothing like it has ever been assembled. Since we're talking about spacecraft heading to an asteroid, I should address the theory that inevitably attaches itself to this. The suggestion is that these are deflection missions dressed up as science, that somebody knows something and is quietly doing something about it. The engineering answer is straightforward. Neither vehicle carries anything capable of altering the trajectory of a 400-metre body. Ramses is an observation platform with a thermal imager and supporting instruments. OSIRIS Apex is a repurposed sample return spacecraft, which is to say a camera platform with a robot arm. The momentum required to meaningfully deflect tens of billions of kilograms is orders of magnitude beyond anything either one could deliver, and we know roughly what such a mission would look like because one has been flown. It required a dedicated spacecraft slamming into a much smaller target at high speed, and the resulting change was measured in minutes of orbital period. But there is something real underneath that theory, and it is more interesting than the theory. Both of these missions are funded in significant part out of planetary defence budgets. The European mission has planetary defence in its name. That is not a cover story. It is the honest structure of the field. The science case and the defence case are the same case, because you cannot defend against something you have not characterised, and characterising it is exactly what science does. There is no separation to expose. Now here is the turn, and it is the thing that reframes this entire section. None of these spacecraft can solve the problem this video is about. Ramses arrives in February of 2029. That is close enough to observe the pre-encounter state from nearby, which is genuinely valuable, but interpreting what it sees requires knowing which model it is looking at, and 2 months of observation from a spacecraft that has just arrived is not going to resolve a period ambiguity that took 2 decades of ground-based photometry to even detect. The spacecraft measurement and the ground-based model are meant to work together. One without the other is much weaker. The measurement that would actually break the degeneracy is not a spacecraft measurement at all. It is a telescope measurement taken from the ground, and it has a deadline. Part 14. 2 windows, and then the door closes. Here is the fact that turns this entire story from a curiosity into a deadline, and it is the opposite of what anybody would guess. Observations taken in 2029 cannot resolve the ambiguity. Not difficult, not marginal, cannot. The paper states it in a single flat sentence. Photometric observations from 2029, they write, cannot effectively distinguish between models A, B, and C. Think about how strange that is on its face. In April of 2029, Apophis will be closer to Earth than any object of its size in recorded history. It will be bright enough to see without a telescope. Every large instrument on the planet that can point at it will be pointing at it. And none of that helps with this particular question, because the geometry of that apparition simply is not suited to separating the period solutions. You will get magnificent data on the shape, on the surface, on the encounter itself, and it will not tell you how many turns the asteroid made between 2013 and 2021. And it gets worse, in a way that is almost elegant. Remember that the 3 families differ by exactly 1 cycle over an 8-year interval. That has a consequence. After another 8 years, all 3 families predict approximately the same orientation again. The discrepancy between them opens up, widens, and then closes back to nothing on a cycle set by the same interval that created it, so you cannot wait them out. The ambiguity is not a fog that gradually clears, it is a gap that breathes. Look at the wrong moment and all 3 models agree with each other, and you learn nothing at all, which leaves exactly 2 windows before the encounter, and they are both narrow. The first runs from February to April of 2027. During those months, Apophis will be more than 60 degrees away from the sun in the sky, which is the minimum separation you need to observe it properly at night. Its predicted mean brightness is magnitude 21.1 to 21.5. That magnitude is the problem. Magnitude 21 is faint, roughly 1,000,000 times fainter than the faintest star you can see with your eyes. To get photometry accurate to 1/100th of a magnitude on a moving target that faint, you need a 4-meter class telescope or larger in the northern hemisphere on a night with good conditions repeatedly. The authors describe the conditions in that window as particularly challenging, which in the register of a technical paper is a fairly loud warning. The second window runs from December of 2027 to June of 2028, and it is considerably kinder. Mean brightness in that stretch runs from magnitude 19.2 to 20.7, between 1.5 and 2 magnitudes brighter than the first window, which in practical terms is the difference between needing the largest telescopes in the world and needing merely large ones. 2 to 4 metre instruments in both hemispheres can do the work. Both windows are wanted, and not only for the period ambiguity. The stated second purpose is to estimate or constrain the yaw perfect. The two unknowns we have spent this whole time on, which family is right and how hard the sunlight has been twisting the asteroid, have the same solution. A long baseline of high-quality photometry across 2 apparitions can address both, because YORP shows up as a systematic drift that will not fit any of the fixed period models. And then there is the sentence at the end of the paper, which is not the kind of thing you usually find in this literature. We encourage photometric observers, the authors write, to take the needed high-quality and extensive photometric data for Apophis in both apparitions. That is an appeal. A group of professional astronomers, having established that the most consequential asteroid encounter in recorded history has an unresolved initial condition, closing their paper by asking the observing community at large to please go and fix it. It is worth being clear about what that appeal is actually asking for, because it is unglamorous. It is not asking for a heroic night of observing. It is asking for a low-cadence, high-precision, long-duration photometry campaign. Many nights, spread over months, on a faint-moving target, producing a single number per exposure. It is the kind of program that has to compete for time against exoplanet surveys and cosmology and everything else, on a target that will generate no headlines whatsoever in 2027, because the interesting thing about it does not happen for another 2 years. That is the real risk here. Not that the measurement is impossible, that it is boring and early and easy to defer. And notice who this appeal is aimed at. Not at agencies, not at mission planners, at observers. The people who produced the data set that made this whole analysis possible were a mix of professionals at national facilities and dedicated observers running smaller instruments, in Chile and Israel and Poland and Morocco and Canada, coordinating across time zones to cover a rotation that takes 11 days to complete. That last detail matters more than it might seem. You cannot observe an 11-day period from one longitude. The Earth turns underneath you, and you lose the target for 2/3 of every cycle. Characterizing a slow tumbler requires a network, spread around the planet, willing to give up dozens of nights each to a target that does nothing dramatic. That network already exists. It has already done this once. The question is whether it gets pointed at Apophis again in time, and whether the large telescopes that the first window requires make room. There is one more thing about the second window that is quietly encouraging. Magnitude 19 to 20.7, from December 2027 through June 2028, is within reach of a genuinely large number of instruments. That is a 7-month stretch, in a brightness range where 2-metre telescopes can produce useful photometry. If the first window is missed, the second is not a consolation prize. It is a real second chance, and it is the one most likely to actually deliver. Last week we looked at a lunar mission where $20 billion of infrastructure planning was resting on a number nobody had ever measured directly. This is the same shape at a different scale. A century of orbital prediction for the most closely watched asteroid in the sky, resting on a photometry campaign that has to happen in the next 22 months, or not at all. Because after June of 2028, the door closes. The asteroid moves into a geometry that cannot answer the question. The encounter arrives with whatever initial condition we happen to have, and then the encounter does the one thing that cannot be undone. It scrambles the periods by a factor of 1,000 and hands back a new state, and the only way to interpret that new state is against a pre-encounter model that we may never have pinned down. There is something almost unbearable about the structure of it. The solar system is about to run an experiment that no laboratory could replicate. Take a 400-metre rubble pile of a composition we can identify, on an orbit we know precisely. Subject it to a calibrated gravitational impulse from a planet whose mass is known to extraordinary accuracy. Watch what happens to the way it turns, from how it responds, work backwards to how its mass is arranged inside, which is a property that cannot be measured any other way at all. That experiment runs once. It runs for about 4 days. It peaks in a window of hours, and the entire scientific value of it depends on having recorded the starting conditions. The story of Apophis was never really about whether it would hit us. That question is closed, and it was closed by good work done in public. What remains is a different question, and a smaller one, and in some ways a harder one. It is not whether we survive the experiment, it is whether we will be ready to read the answer when it runs, which leaves one thing to watch, and it is more mundane than anything else in this story. Somewhere in the next few months, telescope time allocation committees are going to receive proposals for 4-meter class Northern Hemisphere observing time in February through April of 2027 on a magnitude 21 target that will not be in the news. Those proposals will be ranked against everything else asking for the same nights. Nobody will report the outcome. There will be no announcement either way, and that decision, made quietly by a handful of people in a room, is the thing that determines what we are able to say about this asteroid for the rest of the century.